Hey class. So today we're going over Objective 2. Sorry, don't know why that was highlighted. So today we're going over Objective 2, which talks about the graph of cosine and its properties. So we're starting off with the same tables that we started off our sine graph with. So think of these tables as kind of like T-charts. So remember back in the day, if you wanted to graph a function like y equals x squared, you could make a t-chart where you just put in an x and see what you get out for y. So for example, with y equals x squared, you would get 0 for y when you input 0. For 1, you get 1, and for 2, you'd get 4. So then you could graph on your xy plane the point 0, 0, the point 1, 1, and the point 2, 4. And this would give you an idea of how to graph y equals x squared. So we're going to be doing the same thing. Just look at these tables as t-charts. And what I want you to do right now is pause the video and try to fill out all of these values in the table. So the y equals cosine x values in each table. So this is what you should get when you fill in all of the values. And what I want to do is I want to highlight this table right here. So this table is a quadrantal angles, and we can use this in order to sketch the graph of cosine. It'll be a rough sketch because it's only 5 points, but it'll be a sketch nonetheless. Before I go ahead and sketch this, I do want to highlight that you can get all these values from the unit circle. So if you were confused as to how I got all these values, just check your unit circle and you should be able to see where I got them from. So let me just scroll down and I'll rewrite those values, but this time I'll write them in the xy coordinates. So our x originally 0, 1. So for an input of 0 degrees or 0 radians, you get 1 as the output. And I'll continue that. So 0, we have pi over 2. And lastly, we have 2 pi into 1. Okay, so this gives us 5 points that we can plot on our xy plane. And this will be a sketch of cosine. So remember that our x is being divided into pi over 2 slices because we're dealing with radian angles here. So when we divvy that up, we should have 4 tick marks all the way up to 2 pi. And our y, our outputs, have a max of 1 and a minimum of -1. So let's go ahead and plot these. The first one is 0, 1, so our x is 0, our y is 1, which makes it this point right here. Okay. Now if I want to continue this, pi over 2 is 0 for the output, and it goes right there on the x-axis. Our pi is -1, so that belongs right there. 3 pi over 2 is 0, and 2 pi is 1. So this is what our cosine function looks like. We just connect these dots. And there it is. So it kind of looks like a U. Okay. Now to get this graph a little bit better, we can go ahead and add all the points from our other t-charts. So if we scroll down, we should be able to see that. And there it is. So here again, we are plotting y equals cosine of x. So our x is still the radian angle as our input, and the y, our output, is now our x coordinate on the unit circle. Okay, so this is all the unit circle points mapped onto cosine x. So one thing that I will talk about now that I may not have mentioned in my previous video is something that hopefully will clarify what I'm talking about when I'm saying, the input is our theta and the output is our y or x coordinate. So remember that in our old definition of sine from last chapter, we use the fact that there's going to be a point on the terminal side of an angle, and that point will have coordinates x, y. So if we call the distance between the center of the origin and this point x, y, r, the definition of sine theta is going to be y over r, because we can make a right triangle here. Then we use the unit circle to make r equal to 1, and that gave us that sine is just y. So now, using the sine is equal to y, we can graph y versus the theta, or versus the input, right? So y versus theta, sine theta. But instead of using theta, now we're going to use x, okay? So this theta is going to give you a different or y coordinate and x coordinate as it changes. So as theta increases, your x and y are going to change based on how much it increases. But once it gets back to its original point, its original terminal axis, or however you want to say it, once it does a full rotation, well, then you're going to get the same exact output. Okay, and this is why we say that sine and cosine are periodic functions that give you the same output as you add 2 pi to your inputs. So yeah, I hope that clarified things. Okay, so now I'm going to move on and talk about the period, which is something I just mentioned. And the period stays exactly the same because we're still dealing with the same constraints, mainly the unit circle. And we're still going to repeat after every 2 pi. Okay. So again, this is the smallest number you can add to any input in order to get the same output. So if you get an output of 1, the way to get another output of 1 is just to add 2 pi to that input, and so on. Okay, so cosine and sine have the same exact period. So again, I just wanted to kind of make an example out of that by giving you something you could see. And what I want you to do is pause the video again and try to evaluate all of these expressions. So when you evaluate all of these expressions, you get -1 for the solution every time. And if you were confused on how to evaluate these, one thing that you can always do is use your calculator. So you can always use your calculator to type in cosine of pi, cosine of 3 pi, really cosine of any angle if you're confused on how exactly to evaluate it. And that'll get you an answer. So this was just an example to highlight the period is still 2 pi for cosine. Okay, so let's move on. So our characteristics of the cosine function are going to be very similar to the characteristics of the sine function. And this is because we haven't really changed much about what we're trying to do. Right? If you think about it, before when I was saying you get your y coordinate when you evaluate sine, here we're just getting the x coordinate when we evaluate cosine. So we're not going to a different shape. We're not doing anything like that. It's still on the unit circle. So the domain is still -infinity to infinity. And again, to highlight why this is, that's because you can keep rotating forever. You can keep adding a second rotation to any angle, right? It doesn't matter. And you can also subtract any amount of rotations from any angle. So that's why the inputs are negative infinity to infinity. The range being -1 to 1 is again talking about the maxes and mins. So the max and min of our output. And again, this is constrained by the unit circle. So the unit circle, if you look at the coordinates on there, there's no coordinate greater than 1 or less than -1, right? So that's the range, that is the outputs that we can get. The function, again, it has the same period, 2 pi. And here with the y-intercept is the first difference that we see. So I want you to think and try to remember what the y-intercept of sine is. And try to understand why, these y-intercepts change. Why is it? Because it's not 1 for the sine. So the y-intercept is 1 here because when we input 0 to our function, we get 1 as our output. So moving on, we can talk about the zeros. And these are 2n plus 1 times pi over 2. Now, I don't like the way they write this, 2n plus 1 times pi over 2. I'd much rather write it kind of like this. So it's n pi plus pi over 2. So I prefer this method, but if you find the 2n plus 1 better, then go ahead and do that. But they're the same thing. I just distributed the pi over 2 to get my definition. Again, these n's are just an integer, so this is just like adding 2 pi k to an angle theta to get a coterminal angle. K can be anything, right? -1, +2, doesn't matter. So those are the zeros of our function. Those are the angles that when you plug them in for x, you get 0 as an output. Okay. Here's another difference with cosine being an even function. So cosine of -x is equal to cosine of x. And what does that mean? So if we look at this graphically, right? So here is just some negative number that's less than pi over 2. Okay, this could be like negative pi over 6 or pi over 4 or something like that. If we look at the same x coordinate right here, but just positive, we see that they have the same output. They have the same y value. So this is the difference between an even and an odd function. An even function has a straight line going through the positive and negative inputs, right? And this is true for even way down here. If you go down here, those are the same y coordinates being the same kind of distance away from the origin. So whenever you evaluate cosine of a negative angle, you can just as easily evaluate cosine of that positive angle and you'll get the same output. Okay. So just a reminder, sine was symmetric about the origin instead of being symmetric about the y-axis like this is. And kind of the beginning of it looked like this. So that's why we call these two different functions even and odd. So here, you can't draw a straight line from one solution to the other, right? In fact, this is going to be some positive y, and this will be some negative y. Right, so that was the difference. Okay. The relative maximums and relative minimums are here. So these are just the coterminal angles for 0 to get the maximum of 1, and the coterminal angles of pi to get the minimum of -1. And those are fairly similar to our sine minimums and maximums, but they are slightly different. Okay, and that is all of the characteristics of cosine. So let's do some examples. So using the graph y equals cosine x, list all the values of x on the interval negative pi, 2 pi that satisfy the ordered pair x 1/2. So in this problem, in this type of example, we're looking for the input, so whatever angle, that gives us cosine of x is equal to 1/2. So look at your unit circle, try to find what angles give an output in x coordinate of 1/2, and then go ahead and write those angles down. So what you want to do is find all the coterminal angles in this range to those angles you wrote down and list them. And that list of angles will be your solution. So go ahead, pause the video, try to figure that out, and then I'll talk about the solution in a second. Okay, so our solutions are negative pi over 3, pi over 3, and 5 pi over 3. So let's talk about how I got these solutions. So the first thing I did was I wrote down the two angles that are found on the unit circle that gave me an output of 1/2. Okay, and those angles are pi over 3 and 5 pi over 3. So then I wanted to find coterminal angles of pi over 3 within the range of negative pi and 2 pi. But you'll notice that if I add 2 pi to pi over 3, this will be greater than 2 pi. So I can't do that. That coterminal angle is not within the range that's been given to me for this problem. Similarly, I could try to subtract 2 pi, but this is going to be less than pi, negative pi, right? The answer will be negative 5 pi over 6, or 5 pi over 3. And since negative 5 pi over 3 is less than negative pi, which is outside of our range, that means that we can't use that solution either. So the only coterminal angle, well, actually, there are no coterminal angles to pi over 3 that are within the range of our problem. So that means this is the only one that we can add to our list for now. So now we look at the 5 pi over 3, and we try to find coterminal angles to this angle that are within the range of the problem. And what I found was that I could subtract 2 pi, so 5 pi minus 3, or minus 2 pi, is within our range. So this is negative pi over 3, which is in fact greater than negative pi, so it satisfies our problem's conditions. However, if I try to add 2 pi to 5 pi over 3, this is going to be greater than 2 pi, so I cannot use that solution. So that means that out of this angle, we could only get one coterminal angle within the range. So since these are our only angles that satisfy both the ordered pair and our range, then these three angles are the only angles in our solution. So that's how we get that. Let's go to our next example. Okay, so I thought we had another example, but all we have left to talk about is the 5 quarter points. So these are the points that I used to do the rough sketch of both sine and cosine x, right? And the main thing about these 5 quarter points is the inputs of 0, pi over 2, 3 pi over 2, and 2 pi, right? So these are the 5 quarter points for our sine of x. And the reason why we call them the quarter points is because they subdivide this graph into quarters. Okay. So the reason why it's important to memorize these points is because we will complicate this sine of x. We'll either add something to it, multiply it by a number, or do something along those lines, maybe even a combination of both. So it might be hard for you to be able to understand how it's changing the function. But if you memorize these 5 points and are able to apply them to a more complicated situation, then you'll be able to at least get a rough sketch or a rough idea of what this new, more complicated sine function will look like. And we have the same thing for cosine. So if we scroll down, we can look at the cosine quarter points. And these are them. So again, they just evenly divide the sine and cosine function into quarters. Okay, and that is everything for this video today. Hope this helped you out. If you have any questions, please let me know, and I'll see you next time.